Now see this sign bit extension topic. So sign bit extension means when we have this sign numbers. Okay, see this. How to explain this? Simple. Let us say you have represented a value as integer, and later you are copying the value into some other data type whose size is bigger. Then what should happen? I'll take it to the basics and I'll come from there. Let's see this. Now if you have the number 0 1 1 0, what is this number? This number is plus 6, right? And now using 4 bits we have represented it. Later if you are trying to load this number onto a register, let us say register is 8 bits, you are loading this entire number onto a register. How do you want to load it? Now if you use the least significant bits and leave out the most significant bits completely, then whatever was there earlier, those numbers will still be there. Therefore you have to make them something so that the value is not lost, isn't it? Therefore you are going to copy it into the least significant bits only, which means 0 1 1 0. Now what are you going to do with the remaining 4 bits? That is the question. That is the big question. Now what do you want to fill it with? You cannot leave it like that because earlier values were still there. Now you have to overwrite them. What do you want to replace it with? So if you want the value to be still plus 6, you know obviously we have to put zeros. So appending any number of zeros to the left of a number doesn't change the value. Therefore the number is still plus 6 only. So this is how it works in case of unsigned. Now I am talking about unsigned or positive numbers. You know, this can be applied. Now what about the signed numbers? Signed numbers means they might even include minus, right? So let us say we are using sign magnitude representation. Sign magnitude. In sign magnitude representation, now how to represent minus 6 in 4 bits? 1 1 1 0 is minus 6. The reason is this 1 is indicates that it is negative, and then 1 1 0 is let us say I have one more 0 1 1 0. Okay. Now this 1 is representing, even I can go with 1 also, right? So let me go with this 1 followed by 1 1 0. This is also minus 6 only, right? Okay. This one represents negative and the magnitude represents 6, isn't it? Therefore this entire number represents minus 6. Now when you are trying to write this minus 6 into a register whose size is 8 bits, now if you are trying to write it into a register whose size is 8 bits, then what happens? 1 1 1 0, and now you have to fill these 4 bits. Now how are you going to fill these 4 bits? If you apply the same method, that if you put 1 2 3 4, then this entire number gets changed, isn't it? This entire number gets changed and the value becomes plus 14, I guess, right? Why did this happen? Because if you watch it, always the most significant digit represents the sign in sign magnitude. Therefore sign is saying that it is positive number, and the magnitude, the remaining bits, is saying that the magnitude is 14. Therefore it is turning out to be plus 14, but the actual number should be minus 6 only. Then what should we do is, we have to take the most significant bit, the sign, and place it in the most significant bit, and the remaining bits we have to leave it as 0, which means if you are talking about this number 1110, which is minus 6, and if you want to represent it in 8 bits, take this sign bit, this is sign bit, take this sign bit and put it in the MSB, right? And the remaining you put them here, right? And now you are having even 4 bits remaining, and these 4 bits, they can be kept as zeros. So this is the convention which we follow in sign magnitude. So remember this, in sign magnitude, whenever we are trying to extend the size of the register or size of the data, then what we do is, we take the first bit, this sign bit, let's call it as a sign bit, we take this sign bit and put it in the MSB, and then the remaining magnitude we put it as it is, and here we fill all zeros. This is how we extend the sign magnitude number. Got it? Now let's see how to extend the ones complement and twos complement numbers. Okay. Now let's see what happens in ones complement. Anyway, for any positive number, this is again plus 6 in ones complement as well, right? So for any positive number, whatever the representation it is, either sign magnitude or ones complement or twos complement, we are always going to fill in the most significant bits with 0. Therefore we are not going to discuss about it, isn't it? So if you want to extend it to 8, you are going to write it as it is, and the remaining 4 bits are going to be filled with 4 zeros. And so for positive number it doesn't make any difference, right? Let's see what happens for the negative number. Now 1001 represents the minus 6, right? Now I want to represent it in 6 bits in such a way that in 8 bits in such a way that the value minus 6 remains intact. Now what should happen is, find out the magnitude of this. Okay, find out the magnitude of this, I mean to say the positive magnitude, and then try to see that positive number itself is actually expanded and find out the ones complement. So what I mean to say is, if this is minus 6, what is plus 6? 0 1 1 0, right? And you try to extend it. So if I try to extend it, it is going to be 0 0 0 0, and now you find out the ones complement, it is going to be minus 6, isn't it? This is plus 6, therefore ones complement is 1 1 1 1 1 0 0 1, therefore this is minus 6. So if you observe it, what we did is, whatever this sign bit is, so sign bit means the most significant bit, the sign bit here is 1, that particular sign bit has been copied into all the bits. Therefore in case of ones complement, whenever you are extending, so we take this sign bit and we copy them into the MSB of the required size. So what I mean to say is, if I have 1001, right, and if I want to put it in 8 bits, we take this sign bit and we put it in all the 4 positions. So 1 1 1 1, and the remaining entire 4 bits are copied as it is, 1 0 0 1. Therefore sign extension in case of ones complement is taking this sign bit and copying it in all the bits, right, and the remaining the remaining number is written as it is. Now that is why do you think that this one works is simple. So if you try to find out the ones complement of this and try to find out the ones complement of this, both are going to represent the same numbers, except that we are going to have zeros in the MSB. See this, if you find the ones complement of this, what is it? 0 1 1 0, right, which is nothing but 6. If you try to find out the ones complement of this, what do you get? 1 2 3 4 4 zeros, and then 0 1 1 0, which is nothing but plus 6. So both are representing plus 6 except for the zeros. Therefore you remember it this way. In ones complement it works this way, and the same rules can be applied even for twos complement also, but for a different reason. I'll show you what the reason is. Okay, coming to twos complement, before talking about sign magnitude, this sign extension, I would like to discuss one interesting property about twos complement. As you know, the twos complement is weighted code. I think you already know this, right? If I have a number 1 0 0 1, this is weighted code in the sense, weight of this one is 2 power 0, weight of this one is 2 power 1, weight of this one is 2 power 2, and weight of this one is 2 power 3, but it is minus 2 power 3, right? Therefore you get it as minus 8 plus 1, which is minus 7. So twos complement is weighted code. First thing is that, and even sign magnitude is weighted code, but ones complement is not weighted code, which means you cannot write any such formula like this. You cannot give the weights to the digits and then expand it. So now the interesting property about twos complement is this. I'll just tell you. Let us say we have a number 1 1 1 0 1, right? So as you see that the most significant bit is 1, we can say that it is negative number. Now what is the value of it? So let's see this one. Now if you look at it, the value of this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, and minus 2 power 4, I'll just expand it. 1 1 1 0 1. I want to find out the value of it. The weight of this is 2 power 0, 2 power 1, 2 power 2, 2 power 3 and minus 2 power 4, which is nothing but minus 16. So if you observe it, the value of it is minus 16 plus 8 plus 4 plus 0 plus 1. So I think you are going to get it as minus 3. You can check it. Okay. So it is 13 and 6 is minus 3. Fine. Now one interesting thing is this 1 and 1, these two when added, this is minus 16 plus 8, right? Therefore it is going to become minus 8. Check this. These two weights when added, minus 16 plus 8 is going to be minus 8. Now if I delete this number, this first most significant digit, if I delete it, then the number is going to be 1 1 0 1. Then it is 2 power 0, 2 power 1, 2 power 2, 2 power 3, right? Now what do we get here? Minus 8 plus 4 plus 1, which is again minus 3, right? Now if you observe it, replacing these two bits by this one is again going to give us the same answer, right? Now if you observe this one, these two bits when added, the result is minus 4. Therefore by discarding this, the number I get is 1 0 1, and now this is 2 power 0, 2 power 1 and minus 2 power 2, which is nothing but minus 4 plus 1, again it is minus 3, right? Therefore if you are observing it, whenever I have many ones in the most significant bits, a chain of ones, I could actually delete all the ones till only one remains and the value is not changing. Are you observing this? See, now if I have 1 1 1 0 1, instead of having these three, I can delete this one and I can delete this one, and still the remaining one is going to give me the same value. You cannot delete this one. So why do you think that it is working that way? So what is the reason behind it? Is simple. Watch it. Now let us say we have a chain of ones like this. A chain of ones like this. Lot of ones and then followed by some number 0 0 and something followed by something. Okay, immaterial. Now coming to 2's complement, the weight of this one is, in case if you are writing all these, if there are n plus 1 digits, assume that there are n plus 1 digits, the weight of this one is minus 2 power n and the weight of this one will be plus 2 power n minus 1, isn't it? Now by adding these two, what do we get? Minus 2 power n plus 2 power n minus 1, I am writing it as 2 power n by 2. So you can pull out 2 power n as common, minus 1 plus 1 by 2, which is nothing but minus 2 power n minus 1, alright, which means by combining these two, the result is going to be minus 2 power n minus 1, which is as good as you remove this, let this one be the most significant bit, then this one bit alone will represent minus 2 power n minus 1. Instead of these two bits combinedly representing minus 2 power n minus 1, even if you delete it, the remaining bit is going to represent minus 2 power n minus 1. So what I mean to say is, in case of 2's complement, you need not have all the bits, all the most significant bits. You can delete them if they are all going to represent the same number. For example, if you have 0 0 0 0 1 0, now what is the value of this? All these are useless. All these three are useless. As you know, the left to the left of any digit number, if you have zeros, then you can delete them, right? But then leave at least one bit. Leave at least 1 0, otherwise it will become a negative number. Even if you delete this one, it will become a negative number, right? So this number is going to be 2 with this or without this. Similarly, if you have 1 1 1 1 1 0, you can delete all these, right, and the value is going to be minus 2. Even if you have all this, the value is going to be minus 2. Even if you don't have all this, the value is going to be minus 2. Now with this observation, I'll tell you how to do the sign bit extension. So what is sign bit extension? We are going to take a smaller number and represent it in a longer number without changing the value of it, which means we are going to take a 8-bit number and representing it in a 16-bit register without changing the value of it. So watch it. So expanding positive numbers is straightforward. All the MSB bits will be replaced with zeros, therefore the magnitude or the sign doesn't change. Now expanding a negative number is somewhat tricky. So for example, if you have 1101, if this is the number, what would be the value of this? 2 power minus 3, it is minus 8 plus 5 minus 3, I think same number, right? No, yeah, 1101 is minus 3. So if I want to expand this into 8 registers without changing anything, then write it as it is 1101, and in the remaining 4 bits you just copy this sign as it is. So 1111. So this is how sign extension works in 2's complement. Why do you think that this one works? Simple reason, any number of leading ones doesn't add or doesn't change the value of the number, right? The entire number is still going to be minus 3. In case of negative, we are going to add all this. In case of zeros, if I have 0101, which is 5 plus 5, and if I want to extend it, then copy the number as it is, and in the least and in the most significant bits you are going to add zeros, right? So this sign bit is copied. So now what we do in 2's complement or 1's complement is copy the number as it is in the least significant part, and in the most significant part you copy all the bits or you replace all the bits with this sign bit. But in sign magnitude 1, you have to copy the sign bit from the most significant bit in the given number to the most significant bit in the result, and in the remaining places you have to fill 0, and in the least significant bit you have to fill the magnitude. Got it? So in case of 1's and 2's complement, operation is simple. I think you understood the reason why this one works. Now using this principle, even converting a 2's complement to normal number is also easy. Let us say if they are asking you that given a number is in 2's complement, what is its value in base 10? If the question is like this, find out the value of this 2's complement number in base 10. So if the question is let's say 3, if this is the number given, and now we are supposed to find out what its value in base 10 is. If this is in 2's complement, now we have to find out the base 10 number, right? Now convert it to binary first. So f means 1 2 3 4, f means again 1 2 3 4, f means 1 2 3 4, and 3 means 0 0 1 1. Now I told you that in case of 2's complement number, if you have a chain of zeros or ones in the most significant part, you can eliminate all of them except 1, right? Therefore I can eliminate all this and leave this one. You are supposed to leave at least this one, otherwise what happens is the given number is negative. If you even remove this one, then the number turns to positive, and therefore the value is incorrect. Therefore these are all not required. So the number is simply 10011, which might have got extended to this using sign bit extension, right? Okay, now what is the value of this? So this is plus 3, right? And this one is, I think, minus 16, isn't it? 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. Therefore it is going to be minus 13. Therefore answer is minus 13. You need not use all this. If you go by the traditional method of converting, it will take a lot of time, because you have to go for 2 power 4, 2 power 5, 2 power 6, 2 power 7, 2 power 8, 2 power 9, 2 power 10, 11, 12, 13, 14. It is going to take a lot of time. So the best simple method is simplified this way. Okay. So this is how we have these sign bit extensions. So why is this useful is in I'll tell you later. In microprocess we have got some instructions where we try to copy a byte into a word. So copy a byte into a word. Byte is generally 8 bits, and a word that generally depends on the type of the CPU, it can be 16 bits. Now when you are trying to copy a number from 8 bits to 16 bits, we have to decide upon what should be the most significant 8 bits. Yes, least significant 8 bits you can fill the number, actual number, but what are you going to fill the most significant bits? that can be dealt by knowing this sign bit extension. So there might be some questions possible on in this. Okay.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So, first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkey's ranking is 400. If you are happy to get into IIT Roorkey, then getting into universities better than IIT Roorkey is easier compared to getting into IIT Roorkey. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.